Hey pre-calc students, welcome to today's lesson, 3.2 notes, day 2. Today we are going to be evaluating logarithmic expressions and solving some basic log equations. So logarithmic equations and logarithmic expressions. All right, the first thing I want to go over is some vocabulary for a log, okay? So a log has a couple of important pieces to it. Every log has a base, okay? So the number at the bottom is called the base. Whatever you're taking the log of, so this is log base b of a, that one is called the argument. Okay, so the small number under the log is the base. The other number that they're taking the log of is the argument. And just so you know, because this is going to come into play in a couple of the later lessons that are coming, a and b can't be negative, okay, which is what this statement is saying, okay? A and b can't be negative. All right, so you're going to hear me refer to the base of a log and the argument of a log a lot, okay? So make sure you know your vocabulary. All right, so we are going to be practicing conversion rules today. So we're going to be converting from log to exponential and vice versa. A log can be rewritten into exponential form by using what I like to call whoop whoop. So you take the base of the log, you raise it to the power of the number after the equal sign. So that's why you have b to the y. And you set it equal to the argument. So the argument ends up after the equal sign. And we're going to practice converting logs to exponentials and exponentials to logs. You can do the same thing with a natural log. Remember, ln is called a natural log. Now, they won't always have the e written out. So just remember, whenever you see ln, you can put the e there yourself. So natural log of x equals y can be rewritten as e to the y equals x, where the argument always ends up after the equal sign. So that's our conversion rule. Okay, so let's practice that a little bit. And then I'll come back and explain the canceling rules in just a second. Okay, so let's just practice the conversion rules for now. The directions say convert from exponential to logarithmic form and vice versa. Since number 1 is in log form, we need to rewrite it into exponential form. So this is what I like to call whoop whoop. So I'm going to rewrite this whoop 2 to the 0 power and then set it equal to whoop the argument. That's it. That's how you convert. Remember, the directions said convert. That's all we're doing, converting. That means rewrite it. All right, the next one says, the next one is exponential. We need to rewrite it into logarithmic. So these tend to be, not always, but tend to be a little bit harder to do. So what I would recommend is already set it up, leave a couple spaces, 3 spaces, one for the base of the log, one for the argument, and then your equal sign. And then you can kind of mimic the whoop whoop. So they have e to the 0 power. So that means e is the base of the log, 0 was after the equal sign, and then 1 is going to be the argument. I'm going to go ahead and just kind of simplify this because log base e is a natural log. So I'm going to go ahead and rewrite it as the natural log of 1 equals 0. You don't have to, but just so you know, on a multiple choice test, you're more likely to see the natural log of 1 equals 0 versus log base e. Remember, log base e is the same as natural log. Okay, so again, we're starting with exponential. We need to rewrite it as logarithmic. So I'm going to kind of already set it up, put 3 blanks, and then set up my whoop whoop. So we have 7 to the third power. That means the 7 was the base of the log, the 3 was after the equal sign, and the argument is 343. Whoopsies, I didn't give myself enough room. I'll just rewrite it down here. So log base 7 of 343 equals 3. And remember, check with whoop whoop to make sure that you did it correctly. I keep saying that the natural log is log base e. Even though they didn't give me the e, you can assume that it's there. So now I can convert it from log to exponential by doing whoop whoop. So e to the 0 power equals 1. Okay, next one. It is exponential. I'm going to rewrite it as a logarithmic expression. So for those, I like to set up my 3 blank boxes and double check it with my whoop whoop. So it's x to the 3/4 power. So it's going to be x to the 3/4 power equals 81. So I'm going to just write it a little neater over here. So log base x of the argument 81 equals 3/4. So log base x of 81 equals 3/4. Make sure you guys read the directions carefully when you're doing your homework, because if they ask you to convert, they're just asking you to rewrite it. They're not asking you to solve. Okay, so we don't need to find the value of x here. We're just rewriting it from exponential to logarithmic form. All right, now we're going to practice canceling rules. Okay, so we're going to be asked to simplify a couple of expressions. Notice that the first canceling rule is about logs. Okay, so the canceling rule with logs says that if the base of the log matches the argument, then the log and the argument, right, total, all of it cancels to 1. Same with a natural log. Remember, the base of a natural log is e. If the base of the log matches the argument, then it cancels to 1. Okay, so write yourself a little note. If the base of the log is the same as the argument, it cancels to 1. If the base of the log is the same as its argument, then it all cancels to 1. That's the canceling rule for logs. The canceling rule for exponential expressions is very similar. If the base of your exponential, so here's your exponential expression, matches the log and its base, then those cancel and you get whatever's left over. So those turn to 1 and then you get left with whatever was still there. So let me give you an example. Let's say you have 3 log base 3 of 7, right? Where the base of the exponential expression matches the base of the log, then the 3 and the log base 3 would cancel and you would just be left with 7. So if the base of the exponential expression matches the base of the log, then those terms cancel to 1 and you get whatever's left over in the expression. So here, let me use a different color. E to the natural log of x is going to equal x. Why? Because the natural log has a base e. And these would cancel and you'd be left with just x. So those are canceling rules. Now you don't want to get crazy with it and just start canceling a bunch of stuff. You got to make sure you actually study these rules. The logarithmic canceling rule says that if the base of the log is the same as its argument, then they cancel to 1. The exponential canceling rule says that if the base of the exponential expression matches the log's base, then you get whatever's left over in the exponent. When the heck would we ever use this? Well, let's take a look. Evaluate each expression without a calculator. Hey, the base of the log matches the argument, that equals 1. The base of the log matches the argument, so that equals 1, but then you still have the 5. So then 1 times 5 is 5. Okay. So think about over here, this previous one, number 6. Right here, number 6. Log base 8 of 8. 8 had a little 1 here, right? So when those cancel, you just get whatever's left over. Here, log base, let me scoot over a little bit in case you guys are still copying those. Okay, so natural log of e to the y. Natural log has a base e. When the base of the log matches the argument, those cancel, and then you'd be left with whatever's still there, right? So then your answer is going to be y, because it's 1 times y. Natural log has base e. When the base of the log matches the argument, those cancel to 1, and then 1 times whatever's left over, 1 times -4 is just -4. If you're struggling a little bit with how the exponent became a whole number, don't forget that one of the properties of logs that you learned last year is that the exponents of a log can be brought down in front. So that's kind of how you can think about this one, right? Natural log of e to the -4th. The -4th can be brought down in front to -4 times. So let me go back to this example. This is a skill that you learned when you were condensing and expanding. So last year you learned this. We're going to relearn it this year later on. So that's why the -4 becomes a whole number, -4, and is not an exponent anymore. So that's why I keep saying you get whatever's left over times 1, okay? Okay, this next one is exponential. The base of the exponent matches the base of the log. So those become 1, and you just get left with, in this case, x, right? Whatever's left over. The base of your exponential matches the base of the log, so that's going to equal whatever's left over. But in number 12, the base of the log is e. That doesn't match the argument. So how are we supposed to simplify that then? Well, I wouldn't ask you to do something without a calculator if it wasn't really truly possible. So in these cases, if you can't use a canceling rule, what we're going to do is we're going to solve it. So we don't know what this is. So we're going to set it equal to x because we don't know. Remember, variables represent unknowns. By writing it as an equation, I can now use the whoop whoop to rewrite it as an exponential. So as a log, it was kind of hard to understand what the answer would be. But if I write it as exponential, it should be a little bit more clear. E to what power is 1? Well, what is the only exponent that can turn things to 1? If the exponent's 0, the base turns into 1, right? So the only exponent that could ever make this expression be 1 is if it's e to the 0, right? So 0 is the answer to this problem. Now, just so you know, the x was never there, right? We put the x there for our purposes, so technically the answer is just 0, not x equals 0, but I don't mind if you leave the x. Why did we put the x in number 12? Because by looking at it, the base did not match the argument. So here's the thing. The base here is e. it has something in common with the argument, right? So take a look at the argument right here. E and 1 over e to the fourth are related, but they're not the same, okay? Remember, the canceling rule says they have to be the same. Okay, so since they're not the same, I'm going to set it equal to x, and I'm going to rewrite it in exponential form. So I've got e to the x equals 1 over e to the fourth. Now remember, they're related. So this looks like the types of problems we did yesterday. I can rewrite 1 over e to the fourth as e to the, what exponent drops the value down on a fraction, right? So hopefully you remember that it's a negative exponent. And then if the bases are the same, the exponents are the same, right? You see how they both have an e? So that means I can set the exponents equal to each other. And the answer is -4. Remember, we put the x there ourselves for evaluating purposes, but technically the answer is just -4, not x equals -4. I will not take off points if you leave the x there, okay? Okay, for 14, you've got log base 2 of 1 over 64. The base does not match the argument, okay? They're different. They have to match if you're going to use the canceling rules. However, they are related, so we're going to use that, but not until we set this equal to x so that we could rewrite it in exponential form. By doing that, this problem now looks like the ones we did yesterday. 2 and 64 are related. 2 to the 6th power is 64. But if you want 1 over 64, that means that you need to make the exponent negative. If the bases are the same, right, if the bases are the same, then their exponents have to be equal. So the correct answer here is x equals -6, or just -6. The base of this log does not match the argument. They're related, but they don't match. So I can't use the canceling rule. Now I'm going to rewrite it as exponential. Maybe that'll make it easier. 16 and 32 are both part of the root charts, or the multiples of, not multiples of 2, but like the chart for the roots, 2 squared, 2 cubed, 2 fourth, blah, 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 blah. So 16 can be written as 2 to the fourth. But remember, the x is already there, the exponent. So I'm rewriting these with a base of 2. That's what I'm trying to say. The base chart. Ay, ay, ay. Okay, 32 comes from 2 to the fifth. So I could rewrite it as 2 to the fifth. As long as the bases are the same, I can set the exponents equal to each other. So I get 4x equals 5, divide by 4, and x is 5/4. If the base of the log does not match the argument, remember they have to be exactly the same, then I can rewrite it as exponential and use the relationship, because 16 and 4 are related, okay? But they're not the same. So if they're related, maybe rewriting it in exponential will help. Okay, so 16 and 4 appear twice on your base table. You can use a base of 2, or you could use a base of 4. So I'm going to use a base of 4. So I'm going to write the 16 as 4 squared, and I'm going to leave the 4 as is, which is technically 4 to the first power. I put the 1 there so that I can set the exponents equal to each other. Now, when would we really need to use the conversion rule? Because we were using the conversion rule previously, just to convert from exponential to logarithmic. Conversion rules are really good to use when you're given a basic logarithmic equation and you're asked to solve. So notice in number 17, we've got a log base 36 of x with an argument of x equals a half. Like this, it's really hard to tell what the answer is, but in exponential form, it's going to be a little bit easier. So 36 to the 1/2 power equals x. I can rewrite the 1/2 as a root using our rational exponent property that we learned yesterday. The square root of 36 is 6, and 6 to the first power is 6. So notice that the x was already isolated, so all we had to do was clean up the left side. Again, if you have a single log and you have to solve for x and it looks a little complicated, rewriting it into exponential might make it easier. So x to the 4/3 power equals 16. This looks very similar to the problems we did yesterday, where we are going to raise both sides to the reciprocal of the given exponent. That allows me to multiply 3/4 and 4/3 to get an answer of 1. Remember, your answer should always have x equals x to the first power. I'm going to rewrite this as the 4th root of 16 to the power of 3. The 4th root of 16 is 2, and then raise it to the 3rd power. Okay, so notice I've been using the whoop whoop, right? Before I can use the whoop whoop for number 19, since I have a single log, I need to know what the base is. So this is called the common log. If you just see the word log, that's the common log. So you can fill in the base with a 10. So now I can do the whoop whoop. There are two types of logs that they don't always put the base on, and that's the common log and the natural log, which is the one that you see in number 20. Okay. So this whole thing is the argument. So that's what you're going to put after the equal sign. So 10 squared equals 4 minus 16x. 10 squared is 100. So I'm just kind of cleaning up both sides. Now I need to solve for x. So I'm going to subtract 4. And divide by negative 16. Now remember, I am expecting you to do this without a calculator, so you're going to have to do a little bit of trial and error over here. 16 times what is going to be 96, right? 16 times 2 is not going to work. 16 times 3, you're going to have to try a couple. 16 times 4, 16 times 5. The correct answer here is 16 times 6 is going to be 96. So the conversion rule of changing from exponential to logarithmic is best used when you have a single log in your equation, okay? So again, the common log has a 10, but the natural log has a base e. Since the base and the argument don't match, rewriting an exponential is a good strategy to use. And remember, if the exponent 0, the base turns into 1, the base turns into 1. So e to the 0 power is 1. Solve for x, subtract 11. Divide by 6. And always reduce your fractions. So both the 10 and the 6 are divisible by 2. So 10 divided by 2 and 6 divided by 2. Okay, feel free to ask for an ATR pass if you want extra help tomorrow. and be prepared to ask me questions if you need anything. Okay. All right. Have a great day, guys. Bye.